So this breakout session will be done by me. My name is Frederik. I'm with Encord. I'll tell you a bit more about that company in a second. Right now, I just want to mention, so we are also like a YC company. We started in, we were at YC with the 21 batch. We raised $50 million by now, Series B. And yeah, I'll be talking about data acquisition for these IRL problems in the multimodal space. So we all already heard a lot of very cool talks on reinforcement learning. I think some of the things we haven't really heard about yet is all the problems where it's really hard to synthesize data. So far we've heard about the text-only problems where you can actually just synthesize text with the LLMs. We've heard about stuff like tables where you can actually build a table from just HTML or LaTeX maybe. But now we'll sort of think about problems where these types of setups are a bit harder. I think, let's just jump into it. So first of all, who are we at Encord? We are providing this multimodal platform for AI teams. So our objective is really to help transform unstructured data into high quality data that is ready for training, fine-tuning, and aligning AI models fast. So what does that mean? It means to have a place where you can have all your data, index it, and find the next relevant batch of data for your training purposes or evaluation for that matter. You can annotate the data, so have humans involved, all the workforce management, all that stuff that sort of comes with that. And then finally, you can also evaluate your models as a function of your data. So find edge cases, what are the properties of the data where my model fails, and then you can just sort of iteratively improve on your data. So this is not meant to be a product pitch at all, so I'll leave it with that, and then we can get off quickly. So one of the things I want to mention here is that we typically don't deal with training models, so I cannot tell you anything about what is the best algorithm for doing reinforcement learning. I cannot tell you anything about what is the best reward function, these kind of things. I think you shouldn't ask me about this. But I can tell you a lot about data and how you can actually think about that in the IRL context. So let's dive a little bit. So I brought this slide, and then I realized that now sitting here in the part of the audience, I realized that everyone knows what it is. But anyway, so this chart basically shows just multimodal LLMs trained with reinforcement learning since I guess you can see them out here. So basically, the DeepSeek R1 point in time, it sort of really spiked. And I thought this was pretty good. So it seemed like a timely thing to have this right now. Cool. So I think I mentioned this, that there are these applications where you can sort of easily come by data. That could be stuff like analyzing charts, right? You could write a piece of code, generate a chart, and then along with the chart, you could sort of have the question and the answer, and you kind of already have the data for training our systems. You can just synthesize it to a large extent. Same goes for physical AI, where you do simulations. Goes for screenshots of code, all these kind of things, and computer use. It's kind of easy to imagine a data pipeline for getting ready for reinforcement learning. But there are other situations where it's typically harder to do that. So that could be stuff like social understanding. If you have a video feed, what is the emotion of the video? It becomes less obvious how to set up these. So that's what we're going to be talking about today. Before I get into deep, just a raise of hands, how many in here have already trained IRL systems? All right, so a fair few. Everyone else, how many of you are thinking about training IRL systems? All right. Cool. Great. So I think this will be pretty suitable. Great. So just as a quick brush up here, what are we talking about when we're talking about this reinforcement learning data? Now I'm starting with this text-only example, just to sort of illustrate where we're coming from, and then we will try to make it multiple. So you typically have this setup where you have to come up with instructions, right? You have to tell your LLM something that it has to do. And then, for instance, we solve an equation, and then what we've done for a long time is the supervised fine-tuning thing, where we would maybe generate a chain of thought, so have actually the derivation of the equation. And then, in the end, we would have an answer. Right? But the really cool thing about reinforcement learning is that you can actually get rid of this chain of thought kind of thing. So you can just only have the answer, and then the system will sort of self-develop this reasoning capability. And this is very nice in theory, but we've already heard, especially from the keynote, that this is really hard, and it's very, very brittle. We'll come back to that in a second. But that's like the promise here, right? It's much easier. You just need the answer, and then the system will figure out its way. So if you want to make that multimodal, it can be very easy. You can turn it into a chart problem, right? Ask a question about chart. Again, you could do this as fine-tuning thing where you sort of give it the reasoning and give it the answer, but you could also just have the answer. So I hope everyone is following me so far. So the exercise in a second will be like how do we actually do that at a high quantity. One more thing I wanted to bring up here is you can actually design these systems for more things than just outputting a string or like a piece of text, which I think is one of these things where we haven't seen much development yet, but I think that's going to be one of these things that is going to show up more. So you could also ask these systems to output coordinates, right? If I want an LLM that points to something, I could ask it to output the bounding box, like the coordinates of where is this thing, and that's very useful in this reasoning context. If I'm not just detecting cats and dogs, but a very particular thing that is related to these cats and dogs, then this reasoning capability becomes much more relevant. I cannot train a detection system that detects every single sort of kind of different thing within the system, but I can sort of have LLM reasoning. So that's kind of one of these ideas where this can be very, very powerful. So the laundry list here is basically we need to find instructions, we need to find answers, and we need to find some sort of logic. We've heard of that already, like you need these reward functions. So I'm just going to touch very lightly on those. One thing that's really cool here for these sort of pointing things or geometric things is that we have all the traditional computer vision tools in our toolbox. So that actually helps us a lot with building good rewards. So we can just like compute the distance between the predicted point and like the real point. So that gives us quite some leverage there. All right. So now I'll take you through a few different data pipelines, and the exercise is basically going to be you try to come up with something, a data set that comprises a lot of examples of something like this. You could have a question saying, identify which of the following sounds can be heard for the longest time. And then you give it like a piece of audio, and then you expect the system to figure that out. And then maybe it's a speaking. So the question is, how do you then build that data set? And this would be one example of like a vanilla pipeline. You could have a piece of audio, you could have a human sit and annotate all the data. So one way that could look is that you have the stream and you have various different things you need to annotate, and then you mark the regions. And once you've done that, then you can maybe send it for a review if you want to make sure that the quality is really high. Then you can, with these purple nodes, they'll be like consistently throughout these slides, the purple nodes will be automation. So things we do with the computer. You can then transform it, right? You can compute all the areas of all the regions, and then you can have the answer. So this is like a very vanilla setup, and you can probably imagine that already here it's kind of there's a lot of human involvement. So let's look at some of these examples where there is more automation and where it maybe becomes a bit more interesting. And so here's the next one. It's one of the ones I think is pretty cool. So suppose you have a video of I picked the furry in this case. I think it's location vibes, I guess. So you want to predict like what's going to be the person's next move, right? So now we're trying to do this sort of video analytics. And you have all these videos of the furry and everyone else playing basketball. So how do you come about having a big data set of these diverse questions of things that people could do, and then the answers? So here's one example. You could do something like this. You take the videos and you use some off-the-shelf VLM, and you get a very detailed description of the video. Then the next thing you do is you take a sort of regular text LLM and you synthesize a multiple choice from that description. Then you pass that multiple choice through review with a human, and you just have the humans do like this: yes, no, yes, no, yes, no, yes, no, yes, no, yes, no, yes, no. Because that makes the humans really, really fast, and then they can get a lot of data very, very fast, and that way you can get very high quality data very quickly. And then in the end, what you do is you take this, let's say, 10-second video, then you chop it so you only have, or like trim it so you only have the first second. And that's going to be the input to your system, and it's going to try to predict what's happening in the rest of the video. So that's another cool application of how you could set up a pipeline that helps you generate the data you need for what you want. Okay. So yeah, and like here, I think the verification is probably pretty simple as well. You can what's predicted to what's actually labeled or annotated. Now, one thing here is I mentioned here that we are setting it up as a multiple choice, right? And that's because of a practical observation. And the practical observation is that it's typically a very good idea to do what is called curriculum learning, which basically means that you want to start with very simple tasks that are related to your end goal, but not necessarily as hard. And then you train your first system on this easier task, or in the first stage of the training, you train on an easier task. And then you make it continuously harder. Right? So you start by creating multiple choice, and then over time you sort of remove the multiple choice part and you make it more open question. Okay, here's the last one. So now we are thinking about object pointing. So this is this thing where I was talking about geometry. And this is actually from a very recent paper, the idea. So here we are asking for we want to ask for a particular thing in the image. So where's the empty plate? Again, I couldn't have a model that knows empty plate from a plate with, I don't know, what is that? Maybe some sort of soup. And then also with vegetables and all other things, right? I kind of need to have a very dynamic system. So here's how it can be done. You take your images, you source them somewhere, and you need these diverse questions as well. So what you do is you get like a very detailed caption. That's one of these things we kind of have solved with open source LLMs already. Then you use a natural language package to get all the object phrases. So all the phrases from the description that actually contain the objects of any sort. It could be anything. Then you can use a model like Grounding Dino. Grounding Dino is a model where you can it's like an open vocabulary detection model. So you can put in any query and it will try to detect the bounding boxes around the thing. But we're going for key points here. We just want to have one point onto it. So we have to do more. We cannot just send a point from within the box because maybe the object is not a square, so we might get unlucky. So the next thing you do is you take another off-the-shelf model, it's SAM. SAM can take a bounding box and produce a segmentation mask. So that's great. And now the only thing you need to do is you need to also sample a point for that mask. So that's like a pipeline where you stitch together a lot of automation to get to some place where you can again say yes, no, yes, no, yes, no, that's first. And again, so this is like one of these ideas where you kind of get really fast, like the fastest you can, to solve a problem that is not just available off the shelf on its own. Cool. And again here, like the verification logic is quite nice because now you can do stuff like intersection over union if you're doing bounding boxes, or you can do like regression laws if it's key. Right. But there is one problem, and what is that problem? I'm gonna just here's the problem so far. So the problem is that this reinforcement learning part, it can't really stand alone. We kind of heard it already. You have to be very careful. It's like either the task is too easy or the task is too hard. So you kind of have to find a way to scaffold your way through the development process. So the way that's typically done is by having cold start data. What does that mean? It means having data to do supervised fine-tuning. Supervised fine-tuning is again just as I mentioned already. It's this thing where we have the instruction and we also have the reasoning trace. So as a final thing, I wanted to mention here, just time, is like how you then get about getting this cold start data. That's the final thing. And I brought this slide. It's a slide I made back in January when DeepSeek 1 came. And I think it exemplifies pretty well how you need to think about the problem of scaffolding. So DeepSeek R1 is actually 3 models after each other that were trained, and then continuously developed on in the following way. So they used GRPO. They trained like a reasoning model, and they realized they could actually get reasoning from just IRL. But the reasoning traces were horrible. Like there was a lot of Chinese, a lot of English, a lot of reasoning that didn't really make sense. So they used a lot of humans and they sort of cleaned the data out. Then they started from scratch, a new base model, no reasoning. Then they trained a new model on these chain of thoughts. So now there's no reinforcement learning here, but then they got a new protocol, right? And then they could use GRPO because it becomes much more stable. And they changed the sort of the rewards to make sure that it's consistent with the language and all these other things they learned in the first iteration. And then you do the same thing again. You sort of collect more chain of thought data. You collect. You keep improving on the model, and maybe you even train like an RLHF kind of thing on top of it to have this human preference alignment as well. And then finally you reach the final model. Right, so exactly the same thing goes on in all the sort of customers we've been working with. They continuously iterate on the data. They make sure that everything they learn from their production systems, it keeps feeding back into the development. It's like an iterative process that has to go on and on and on, and you have to obsess about the data and improve it continuously. Okay, so as a final thing here, just trying to somehow make a decision for how do I get about getting this full star data. And I think the first thing you want to ask yourself is, like, can I find a cool chain of thought data set somewhere out there already that is somehow aligned with what I'm trying to do? If I can, then I'm going to leverage it. Either I'm going to apply all the rules that I can. For instance, if it's code or graphs, I have a lot of sort of knowledge about the structure, so I can apply templates and maybe I have a human review the data. If I don't have this structure, then maybe I can use off-the-shelf LLMs, for instance, to generate traces that make sense for this particular type of data. And then I can clean it with reasons. If I don't have these sort of, let's say, open source data sets, that's like an umbrella term here, then I need to collect raw data. And hopefully I have a system already or like an approach for getting raw data. And when I have that, then I need to come up with like a really good pipeline. And if I can come up with a pipeline like the one we saw with the bounding boxes and masks and all these things, I'm going to do that and I'm going to send it through the review. If I cannot come up with like a smart pipeline like that, I have to resort to something else. Maybe I have users in my system already, or I have another system that I can sort of piggyback off of. Then I can collect a lot of logs and like user experience. And that typically helps me sort of take that and synthesize it into research. A good example here could be in the medical space, right? If you have a CT scan, you probably also have doctor's diagnoses on the scans. So you could take that and turn it into like a reasoning trace. And finally, you might have to just have some sort of interactive way of funding models such as Okay. So this is essentially how the picture looks today, and I hope it's going to be even more advanced and even easier to create this data. But I hope it's clear from what I've told so far that everything we've seen, at least from our side, is that you have to iterate very, very quickly and iterate a lot of times, continuously improve on both all the sort of reward system and all this, but also like really obsess about the data. I saw a job post yesterday actually from some of the early employees at here. They're starting a new company. And one of the things it said in the job post was that everyone in the ML team, the senior engineers and the juniors, they all know our data set by heart. So just a thing to keep in mind. Data is just really, really important. Okay, so that was basically what I wanted to tell today. I hope it's been somewhat inspiring in terms of how you might set up pipelines for your data, and how you might be able to hack your way to a good data set. Of course, there's a big thing, evaluation, all these kind of things that I'm going to leave that for another day. The last thing I want to mention here is that if this was interesting and you want to learn more, then I'm actually writing up a white paper that has much more detail on all these topics. Also, like a really good reading list. I have a lot of like really good papers on the list. So you're free to contact me if you want to learn more. There's also another thing on evaluation, which is rubric evaluation. We have a pretty cool white paper that is full of this. Otherwise, I think this is time for questions.